Uh, okay, this is our first talk by JV, and he'll be talking about infinite matrices. So go ahead.
Thank you, Alex, for the introduction. So, as he said, I will talk about a little bit a recent topic I'm working with my supervisor, George Willis, in my PhD, and Stefan and Colin as well, as my co-supervisors at the University of Newcastle. So, first of all, to give an outline of how our talk will be, the main idea, the main objects that we are trying to work with them. At the moment, we are working more on the ring theory sense of things, but the idea is that we want to use the units group to generate some interesting group for us with some interesting properties. And we have one group theoretic result at the moment. So on our talk today, I will begin with some basic definitions of things that will be useful for us. Then I will talk about what are these infinite matrices. So the idea is that they are always indexed by posets and use some poset structure to define them. And then I will talk about one of the results that I'm working recently about the duality that these rings have with the category of posets. So first of all, for the basic definitions, the first one, I think everyone knows what a partially ordered set is, but just to be sure that everyone remembers the definition. I will call lambda a partially ordered set if there is a two-array relation between two elements on lambda, such that we have three properties being satisfied. So for our A, B, and C, A is less or equal to B less or equal to C implies A is less or equal to C, which is transitivity. We have for our A and B, if A is less or equal to B and B is less or equal to A, then A must be equal to B. And for our A, we have that A is less or equal to A. And we will meet the less or equal sign when we are talking about a poset, even though here I wrote before, but yeah. And we have a lot of common examples that we know, like naturals, rationals, reals, integers. They are all posets with some order, the usual order. And now for another important definition for us, given lambda poset and two elements that are comparable to each other, S1 and S2, we define the interval S1, S2 as all the elements that are between S1 and S2, including S1 and S2. And we will say that lambda has finite intervals if for every element S1, S2 that are comparable, this set is finite. And this property, like all the posets that we will work here, they will need to be have finite intervals, so we can define the multiplication of the ring property. Later, you will be able to see why a little bit. And then for convex subsets of our poset, we will say that a subset is convex if it's closed under intervals. So let's draw a little bit to explain both ideas. Here I will draw a simple poset. Here we have 1. Here I will call this element 2. Here I have 3. Here I have 3 prime. Here I have 4, and here I have 5. So as you can see, there are some easy posets. You have 1, 2, and 4, 5. These are intervals. 1, 2, 3 as well will be an interval. 1, 2, 3 prime will be an interval. But for example, if we get from 1 to 4, we need to get the things above and below, because the interval 2, 4, for instance, is 2, 4, 3 prime, and 3. So I think here it can be a little clearer what convex sets can get extra and intervals can get extra. Like you don't have only kind of linear things. For example, in the integers or the naturals, you can have more parallel stuff around. And last but not least, we also have the definition of reducible posets. So we'll call a poset reducible if we have two non-empty subsets of this poset, such that the poset is the union of both of them, and the intersection of both is the empty set. And for all elements in the first one and element in the second one, they are not comparable. So not comparable is that you cannot say S1 is less or equal to S2 or S2 is less or equal to S1. In this case, we will denote lambda as being the disjoint union of lambda 1 and lambda 2 because they are not comparable. And we will say that lambda is reducible otherwise. So for another simple example, we can just get the poset with elements 0, 1, 0 prime, 1 prime. So it's clear that the elements on one side and in the other are not comparable at all. And the union of both of them will give the entire poset. So I think with this, we have the important definitions that we will need to work using posets. Now we can go for the formal definition of these matrices rings. So what is the idea? We first get a ring and we get some poset with finite intervals. And we will define this ring tri lambda p, which is like triangular matrices indexed by lambda and with entries on the ring P. So they will be the elements of the square matrix lambda times lambda. So you just have a big square matrix here, and lambda can be finite or infinite with any cardinality. And if S2 is less than S1 or S1 is not comparable to S2, we will say that the coordinate will be 0. Everywhere else it's 3, but on these coordinates, it needs to be 0. The sum will be given coordinate-wise, and the multiplication will be given by this formula here. So as you can see, the formula uses the interval structure, and for the finite matrices like this will be the same formula. So, and from now onwards, we will denote the elements of these rings with capital letters, A, B, and C. And if we want to specify a coordinate S1, S2 in lambda, we will write A S1, S2 to specify the coordinate. I think through the definition, it's quite formal and dense. So let's give an example that might be easier to see what's happening. Here, let's our lambda, our poset be the natural numbers, excluding 0, and order given by A is less or equal to B if B is a multiple of A. And P, as always, can be any ring. Here we are not specifying which ring we have. So the general elements of our matrix will be these ones. As you can see, these elements, the coordinates that can be non-zero, the first element divides the second one. So here, 1 divides every natural number, so it's all good. 2 divides 2, 2 divides 4, 2 divides 6, so these coordinates can be non-zero, and so on for all the other elements. And the multiplication will be given this way. So just open it up. Like the diagonals will just have multiplication over the diagonals. And this one would be, for instance, A12, A11, B12, plus A12, B22. So you just change this middle coordinate through all the things that divides the second coordinate on this case. So here we went through an example. Next, let's see. One of the interesting properties that these rings have is if you have a poset with finite intervals and P an arbitrary ring, then given a convex subset of your ring, you can get an ideal such that the quotient of the ring over this ideal is just the, how do you say? It's isomorphic to the symmetric, to the convex set, the ring defined by the convex set. And going back just for the example below, what this result does is here we have intervals, for example, 1, 2, we have the interval 2, 4 in this example, or 1, 4. And what is it doing? I am able to kind of cut these matrices and work only with finite matrices in this case. So here the 2, 4, it will exclude this one, like this coordinate would be 0. You would only have a kind of 2 by 2 matrix. And yeah, it's just a way to, with this result, we can kind of work the multiplication of our matrices in finite subsets if we make our convex set just finite. And these results also bring us to how we can put topology on our studies. So if you have a poset with finite intervals and P an arbitrary ring, then the ring of triangular matrices indexed by our poset will be just the inverse limit of all the ones that are indexed by the finite intervals. And with this result, like for the ones that are used with inverse limit, we can, if P is a topological ring, we can give a topology to this bigger ring. And in case that P is pro-discrete or profinite, then our tri-lambda P will also be profinite or pro-discrete. And with this, there is also, going for the group side of things, the result that might be interesting for some of you. Given a P a ring and lambda a poset with finite intervals, we can define the following. So tri-star will be the units group of our ring. So they are all the matrices A, such that exists P in tri-lambda P, such that A, B equals the identity. So identity here will be just a matrix with 1 on every diagonal, right? And we will define the almost triangular matrices, A tri-star, lambda P, as the group of matrices that accept finitely many other coordinates to be non-zero. So going back to this example here, the A tri n star P would also accept like finitely many of these coordinates that were originally 0 to be non-zero. And it's still, the matrices are still inversible in this case. And what do we get with this definition? Given lambda an irreducible infinite poset, so that's why irreducible was important to define, with finite intervals, and F be a field with the discrete topology, then the quotient of this group over its centers is a topologically simple group. And if lambda is countable when F is finite, then this group will be a totally disconnected, locally compact set countable group. So this was one of the central results for me to study this, because George had a result with one of his students that was way less general than this. Like you had many other conditions, but this one I just generalized it for many other posets. And then I was just working without the other theory around as well. And an open question that I still want to work, and it's also related to why I'm working with the duality problem now, is can I solve the isomorphism problem for these matrices? Like, is it possible for different posets to give the same simple group, or will they always give different simple groups? And with this, I think we are done for the matrices and the ideas. And now I will talk about a little bit of more recent stuff that I'm looking at. And first of all, some of the results that made me think that this duality really exists. And for that, I need to define what a product of posets is. So given two posets, we will define the product poset as the poset with elements in the product space. And in order given by S1, S2 less or equal to T1, T2, if each of the coordinates is less or equal than the equivalent on the other one. So for example, if I get lambda1 and lambda2 to be the simplest set that we can get, 0, 1, then the product will be just this square thing, 0, 1 prime, 1, 0 prime, and 1, 1 prime. Okay. So there is an error here. And what can we get when we have this result, when we have this definition, is that if we have two posets, lambda1 and lambda2, and P any ring, then having the product inside our matrix, having the product on our matrices ring is the same as kind of composing this tri-lambda in some way. And here again, with the same poset that we had before, it's an example. So the matrix above would be for tri 0, 1 times 0, 1. And the one below would be tri 0, 1, tri 0, 1 P. So here, as you can see, each of the coordinates will be in tri 0, 1 P. And you also, after that, index everything by 0, 1 P again. And let's see. And the next result as well, I think this one was the main one to think about the duality problem. So if we have two posets with finite intervals and P and ring, in general, we can define the disjoint union as we defined before. We just put the posets parallel to each other. The elements will be of the disjoint union of both posets, and they are not comparable between themselves, but they have the same properties that they have before. And here, like this is more like a coproduct in the category of posets, and it becomes a product in the category of our triangular matrices. So this was the first result that made me think that there might be a duality around here. And an example would be if you have the set 0, 1 again with all the 0 less or equal to 1, then here we would have the ring on the left, try lambda 1, disjoint union lambda 2, and here we have the ring on the right. And let's see. Now to really start working on the side of the duality stuff, I need to define some things. And the first of them is what is a homomorphism of posets? So given lambda 1, lambda 2 posets and f a function between them, we say that this is a homomorphism of posets if given S1, S2 in lambda 1, then S1 is less or equal to S2 if and only if Fs1 is less or equal to Fs2. I think but what I was thinking yesterday, I only need a then here, but at least for all the other results that I proved this, I can use this way as well, and I wouldn't have any problem. And another definition that will be important is we say that this is a convex homomorphism if convex sets are mapped to convex sets. So why do we want convex homomorphism? Because, for example, we have integers. We can define this function on the integers. We send n to n, right? As you can see, it satisfies the property before. Like if S1 is less or equal to S2, then Fs1 is less or equal to Fs2. But the problem of this function is that we cannot define there is no way to define a proper function from try ZP to try ZP that still maintains these things for some reasons, like we cannot make this function continuous. And the first result that we had, this was one of the central results to finally be able to start proving things about the duality, is if we start with a ring that has only 0 and 1 as idempotents, So just to remember, idempotents are elements such that a squared is equal to a. Then two of these matrices rings will be isomorphic if and only if the posets are isomorphic themselves. Under the homomorphism idea. And for here onwards, because most of the results that I proved about the duality, I'm trying to maintain this structure that we have of idempotents being related to the poset structure. So we will still ask that P has only 0 and 1s as its idempotents. And the first result that I got, this one Stefan already saw, but given F convex surjection between posets, we can make a function from lambda tri lambda 2p to tri lambda 1p that will be an embedding in such a way that we preserve the order property on the idempotent. So we still have all this structure that we have that can be translated to the idempotents. And another one is on the opposite side. If we have a convex embedding, this was the problematic one that I had, but I was finally able to write it down like in the last 2 days. We will have a surjection from tri lambda 2p to tri lambda 1p in such a way that we also preserve the order on the idempotents. So now what I'm trying to do is using these 2 results, I want to finally be able to create a functor from the category of posets to the category of our triangular matrices indexed by a fixed p. And then what are the next steps that I want to follow with this stuff? So the first one is the one that I was talking about. I want to use the last 2 results to prove the existence of a functor from the category of posets with convex. Like the homomorphism on my poset category will be just convex homomorphism to the category of, here it was supposed to be tri blank p. There is a typo. I want to also get the converse as well, because the converse seems kind of not that hard to do. Like I still need to finish some steps, but the idea would be P with only 0 and 1 as idempotents. I can also get back the poset structure. And also if I have a function, I can translate it to a function between posets and also inverting the arrows. Finishing with that, like I have a result about the isomorphism problem of these rings. So I want to try to translate it a little bit to the group side of things and maybe work a way to talk about the simple groups being isomorphic or not. And last but not least, also use this duality structure to create more groups by being able to work with the posets more freely, like using more of the properties that I can have on posets. One of the ideas that George talked a long time ago was trying to define a quasi isomorphism on these posets and stuff like that. And maybe with that, being able to easier work on what this will do on the groups. And yeah, that's it what I have for today. Let me praise. Oh. Thank you. Okay, I spent 25 minutes almost.
Okay, let's thank the speaker. Are there any questions for the speaker?
I could ask one. So you create these totally disconnected, locally compact groups.
Mm-hmm.
And you want to know which ones are isomorphic or homeomorphic or whatever it is for that object. So do you know how to compute the scale?
I don't know. I think I didn't try to do that yet, even though George always works with the scale. I don't think I did.
Because that would be a way to distinguish which ones are different.
Mm-hmm. Because I know one condition that we have for it being isomorphic, and you can prove it easily by looking at how they are defined. It's just looking like if posets have, you have two posets. No, it don't need to be posets. Actually, on the poset case, I don't know, but I know for the posets case, like when you forget which property, because we can define these groups by forgetting the second property. Like we can have elements that are symmetric to one another. And for these ones, I know a condition, but yeah, for posets, I don't know. It might be good to compute the scale function, but I would guess that it will only make a difference for countably many of them at most.
Well, yeah, because it's an integer. Yeah.
Yeah.
So is it true that the A tristar groups are generally non-compact?
I think if you don't make P finite, they won't be locally compact.
Won't be locally compact.
No,
Won't be locally compact or won't be compact?
for A tristar,
Uh-huh. They are the
if-
ones that Mary asked about, right? The simple
Yeah.
groups.
but if lambda is infinite, then it's not compact.
Okay.
Because this is similar to when we do the Rift product kind of thing. Like you are forcing something to be an open compact subgroup, but then you are add countably many things through extra on your basis in some way.
Yeah. Okay.
And it's a direct union of things as well.
Okay.
So we have 1 minute till the next talk. Are there any final questions? Okay, in that case, let's thank the speaker again. Thank you, and I'll end the recording.